Homework 11, section 6.1, discrete random variables, video 3. Let's see if we can construct a probability distribution for this random variable where you roll a pair of dice and you want to let S equal the sum. Then we're going to follow through with some more probability questions. I better make a note to myself. Follow through with probability questions. All right, if we're going to make a distribution table for S, we need to ask ourselves two questions. The first question is, what are the possible values of S? If you roll a pair of dice and add up the numbers, what is the least sum that you can get? If you roll a pair of ones, you can get a 2. What is the greatest sum you can get? You would have to roll a pair of 6s. That greatest sum would be 12. And I can obtain every sum in between. So our possible values for S are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Now, this would be a little trickier to do straightforward because for certain sums, there are a variety of ways to get them. For example, to get a sum of 4, I can roll a 1 and a 3, or a 2 and a 2, or a 3 and a 1. Some sums are easier, like 12. There's only one way to get that, a 6 and a 6. So instead of trying to brute force our way and calculate each individual probability, let's see if we can look at the sample space. However, I would not recommend doing a tree diagram because think about how a tree diagram for rolling 2 dice would go. The first set of branches would have to represent what the first roll could be, which would be one of 6 values. So it's either 1, 2, 3, 4, 5, or 6. But the second dice could also be 6 values. So from each of these 6 branches, I would have to branch off 6 times, and there would be a total of 36 branches. It's not impossible, it's just not very practical. So how can we find the sample space without using a tree diagram? Well, when your experiment consists of 2 steps, in this case rolling the first die and rolling the second die, you can create a table to capture all of this outcomes in the sample space. In this case, we could create a table where the column on the left will represent the result of the first die, and the top row will represent the result of the second die. So 1, 2, 3, 4, 5, 6 is how the first die could come out. 1, 2, 3, 4, 5, 6 is how the second die could come out. And we are interested in the sum of the die, so I'm going to put a plus up here in the corner. This is just an addition table. To keep it a little organized, I'm going to draw a line that cuts each row and column in half. So 1, 2, 3, 4, 5, 6. And then we're just going to fill in all of the sums. So going across the first row, 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4, and all the way across. So 2, 3, 4, 5, 6, 7. And then the same thing for the next row. If I add 2 to the numbers 1 through 6, I get the numbers 3 through 8. 3, 4, 5, 6, 7, 8. It's just an addition table. 4, 5, 6, 7, 8, 9 is the next row. 5, 6, 7, 8, 9, 10 is the next row. 6, 7, 8, 9, 10, 11 is the next row. 7, 8, 9, 10, 11, 12 is the final row. Now, we are assuming equally likely outcomes, meaning it's just as equally likely that the first die is a 2 as the first die is a 6. Or it's just as equally likely that we get this sum of 6 here as we do this sum of 5 over here. So how many sums are there? Well, 6 times 6 is 36. And now all we have to do to calculate our probabilities is count. So for example, if we want to know the probability that the sum equals 2, we know it's going to be out of 36. So we just have to go find how many 2's are in our table. And there's only one of them, right there. So there's a 1 out of 36 chance that we would roll a 2 when we roll a pair of dice. We could turn it into a decimal, but that's just a matter of using a calculator. We'll leave it as a fraction. What's the probability that the sum equals 3? Well, it's something out of 36, and we have to find all the 3's. There's 2 of them right there. So 2 out of 36. I'm going to go ahead and reduce that to 1 out of 18. And of course, we could turn that into a decimal. And we could do the same thing with all of them. Probability the sum is 4. Probability the sum equals 5. Probability the sum equals 6. Probability the sum equals 7. Probability the sum equals 8. Probability the sum equals 9. Probability the sum equals 10. Probability the sum equals 11. And the probability that the sum equals 12. And we know that all of these fractions will be out of 36. So we can get this set up, we can get a lot of this set up before we even go and look back at our table. And now we just got to start tracking down some numbers. The probability the sum is equal to 4. Here's all the 4's conveniently located diagonal to each other. 1, 2, 3. 3 out of 36, which would reduce to 1 over 12. The probability the sum equals 5. Here's all the 5's. There are 4 of them. 4 out of 36, which would reduce to 1 over 9. The probability sum equals 6. All the 6's are diagonal from each other. 1, 2, 3, 4, 5. 5 out of 36, which won't reduce. We just keep getting more and more. The probability the sum equals 7. There are 6 of those. 6 out of 36 reduces to 1 over 6. But you'll notice what happens after 7 is that they start going back down. If you count the 8's, there are 5 of them. So 5 out of 36 is the probability that the sum is 8. And again, the counts will keep going down. 4 9's, 3 10's, 2 11's, 1 12. 4, 3, 2, 1. And we could reduce these fractions, but that's not really the main point I'm trying to make. The point I'm trying to make is that in some experiments, especially experiments that consist of 2 steps, it's easier to make a table than it is to make a tree diagram. So there's our probabilities. And which sum has the greatest probability? 7. I don't know how many of you have ever played craps in a casino, but there's a reason why 7 is a special sum. It has the greatest probability of occurring out of all the sums. I did say that I want to do some follow-through questions. So let's assume that we already have this table, this distribution table set up, and I'll be focusing on the unreduced fractions. Let's say you roll a pair of dice and you want to know the probability that you roll doubles. Actually, let's not do that one. I could do it. I would just need to look over here and count how many of these sums represent doubles. Double 1, double 2, double 3, double 4, double 5, double 6. So 6 of these 36 represent doubles. But I want to do a probability in terms of the random variable we're looking at. For example, let's say you're playing a game and you need to roll a certain number to get to the end of the path and win, and you're 10 spaces away. So what's the probability that the sum is greater than or equal to 10? Well, don't overthink this. The probability that the sum is greater than or equal to 10 means that I want the sum to be 10 or 11 or 12. Emphasis on the word or, because or means add. The probability that we roll a 10, 3 out of 36. The probability that we roll an 11, 2 out of 36. The probability that we roll a 12, 1 out of 36. And if you add all those, you get 6 out of 36. So there's a 6 out of 36 chance that when I roll a pair of dice, it will be 10 or greater. What's the probability S is odd? In other words, that we roll an odd sum. Well, the sum could be 3, so it's 2 out of 36. Or, plus, the sum could be 5, which is 4 out of 36. Or, plus, the sum is 7, which is 6 out of 36. Or the sum is 9, which is 4 out of 36. Or the sum is 11, which is 2 out of 36. 2 plus 4 plus 6 plus 4 plus 2 is 18 out of 36. Hey, that's exactly 1/2. There's a 50% chance that when you roll a pair of dice, the sum is odd. What's the probability the sum is even? The other 50%. Rolling an even sum would be the complement of rolling an odd sum. And remember that the sum of the probabilities of an event and its complement is 100%. So the probability that it's odd is 1 minus the probability it's even. So 1 minus 50% is 50%.